My name is Ivan, and our topic today is Architect Guide for Apache Ignite, AC transactions, and consistency. A couple of words about myself. I am employed at GridGain Systems. I'm leading data consistency developers team. Also, I'm Apache Ignite committer. Basically, my contributions and my current area of responsibility is directly related with transactions and data consistency. So, what I'm about to tell you today, I participated in those contributions, and I will share my experience. I will not present you today what is Apache Ignite. I think most of you already know. What is it? I will shortly say that it is a distributed data storage. It stores your data in a distributed way, and it can be accessed with several ways, with Gcache API or SQL or even thin clients on different languages. And when you plan your solution, there's always a trade-off between data safety and consistency versus performance. You have to make the choice, and the choice should depend on your use case. And Apache Ignite can serve in many use cases. It can be used as cache layer for external storage. It can be also reliable key-value storage itself. It can even be used as a business critical transactions processing core engine. And in any of those use cases, Ignite configuration is flexible and allows to adapt for every use case. And in our today's presentation, I will tell you the most crucial configuration parameters which you should consider if you plan to use Apache Ignite and go to production. So here's a list of the most important configuration settings from my point of view that are worth being reviewed between planning to go with Apache Ignite. First one is data replication modes. They are known keywords as partitioned versus replicated caches that are used in many distributed systems. I will tell you the differences and will tell how to configure it. Next point is data sync guarantees. Next one is data consistency. And the last one is data storage. And if we are talking about persistence and persistent caches, we will discuss disk-based consistency. Let's start over and let's start with data replication modes. In Ignite, you can specify data replication mode with set cache mode method of cache configuration bin. There are two modes. First one is partitioned. In this mode, data is partitioned. Every key is mapped to a single partition, and number of partition copies for every partition can be specified. Next option is replicated cache. As you can guess, in replicated mode, every node keeps whole dataset. By default, if you're using partitioned cache, every partition is present in strictly one copy, and this can be dangerous because in case one node will leave, you may lose your data, but you can configure desired number of backups. For example, if you will pass one, as you can see on this example, partition one is present in two copies. And when there are backups, there are also primaries. There's always a primary partition, which is responsible for coordinating and synchronizing access to your data. If primary leaves, then primary is reassigned to one of your backups. And comparing partitioned and replicated cache, if you perform a put in partitioned cache, then it goes to the corresponding node that owns your partition in which data should belong. And writes are quite fast if you're using partition cache because you then don't have to propagate your updates to all cluster nodes. And on the contrary, reads, if you perform a read, may write a network hop because if you're performing read even from a server node, it can't. There's a chance that it don't possess the data that you need, and it will require network communication in order to get needed data. And about capacity planning, if you, for example, have 100 gigabytes of data, total in cluster, you have to multiply this value by backups plus 1. So if you have one backup, then 100 of gigabytes of your data will turn into 200 gigabytes among the whole cluster. When you work with a replicated cache, when you perform a put, data will be present on all cluster nodes. That instantly implies that writes are heavy because you have to propagate your data to all cluster nodes. You have to communicate with each node, which may create additional load to cluster. And on the other hand, reads are instant. For example, if you write code that should access your data from a server node, you may be sure that it will work fast because you can read your data on the same nodes that your code is working, which is good. And perhaps if you have a cache that is accessed really often, you may consider using replicated cache. And storage space multiplier for replicated cache is number of nodes. So 100 of gigabytes of data in cluster of 4 nodes will turn into 400. And if you want to choose which type of cache you want to work with, consider that partition cache is good for cases when you perform a lot of writes. Writes are frequent and reads are not such frequent. For example, it can be storage of your transactions or some operational data. And on the other hand, if you have a not very big set of data that is often required, but data that is not often updated, good choice would be a replicated cache. I think good example here is dictionary. So dictionaries don't get modified really fast, but you may need them for lots of your operations, or for example, static, currency conversion rates or something like that. A small set of information that is needed for lots of your operation. If that's true, I think replicated cache is good choice. Let's proceed to next point. I think it's more complex one, and let's talk about data sync guarantees. The question is when we are talking about data sync guarantees is when the system assumes that your updates which you have executed is completed. So consider an example when you're working with Gcache API and you perform cache put. You put key 1 and assign data as value to that key. And when you do this put, system hangs for a small period of time, and then it returns control to the thread from which you execute this operation. And when the system returns control, system assumes that your update is completed. And the point of time when the system assumes that the update is completed is also can be configured. Let's review possible options of guarantees which you can choose if you want to configure data sync. It's configured with set write synchronization mode of cache configuration, and there are 3 modes. First one is default. It's called primary sync, and in primary sync, client will wait for data update completion only on primary node. Softer option is stricter option is using full sync guarantees when client will wait for data update completion from all participating nodes, including primaries and backup partitions. It's not a common case, I think, but in some cases you need to demand full sync guarantees from your cache, and a few slides later I will show you an example when this is crucial. And the option with the least number of guarantees is full async. As you can guess, client doesn't wait for data update completion at all. I will show you an example how data flow is propagated inside the cluster when you perform a cache put. And every part, every stage of this message communication will be enumerated in stage. So right now we are on stage 1. Nothing has happened yet. Only client has performed the put, and corresponding request is propagated to primary partition. And I will show you on which stage in each write synchronization mode, user thread will be unlocked and will be able to proceed with further operations. If you are using full async, thread will be unlocked directly on stage 1. So it doesn't actually wait for anything. When you perform a put, you are free to proceed making another puts. But if you are using primary sync or full async mode, thread will be still locked until client will receive some acknowledge messages. After stage 1 comes stage 2, when data is actually written into data storage on node 4. Node 4 is owner of primary partition, partition 1, in which key 1 is to which key 1 is assigned. And stage 3 is a response from primary node to client node that update on primary node is successful. And at this point, user thread is unlocked, so you can proceed with your another puts if you are using primary sync. But for full sync mode, this is not enough. And after that, after receiving update from client and after acknowledging client, primary in a synchronous manner sends update to backup node about the fact that key 1 should be updated as well. At some point, node 1 accepts these requests, this request, updates corresponding key, writes it to its own storage, and responds client that as well update was written and client should be acknowledged that it's true. And on this point, at stage 6, thread is unlocked if you're using full sync mode. So if you are using structure mode, your latency on operation is increased, but you gain structure guarantees about point where control is returned, and at this point, how much nodes have updated their data. One also important configuration parameter is whether or not you can read from backup partitions. By default, it's true. And I think in most cases, you have to keep it as true, but you can disable it. And if it's enabled, read operations are balanced between all partition copies. And on replicated caches, there's guarantee that reads will be performed locally. Let's consider an example where full sync mode may be required for your case. Remember, we are on stage 6 where we have performed a put and we got an acknowledge from all participant nodes that update actually was processed. Imagine that this put is only part of your more complex business operation that includes more actions and probably actions outside of Ignite system. Consider an example when there's a pipeline, and after performing this put, you have to send message to your external system that that is part of your complex business operation. For example, system, and after that, your pipeline flow may return back to Ignite, and there's no chance that it will be processed by the same client. It can be routed to any Ignite node, and the next pipeline step of your complex business operation will work only if your data that will be updated at this point will be available. So in case such complex logic is implemented, there's a guarantee that if you are working with full sync mode, that's wherever this message can be traveled and wherever it can be processed. Next pipeline step, if it will access any Ignite server node, it will see the data, it will see the updates performed during this cache put, because their strict happen before guarantees. So unlock of this thread happens before all updates on your all partition, and this pipeline steps happens before this pipeline steps, which in turn happens before acknowledgement from cache put, and such there's a chain which guarantees you the presence of your update on all cluster nodes. So if your
pipeline operation is more complex than just single puts, perhaps you will need the happen before to see your data available in case there's a chance that you will read it from another node. Let's proceed to data consistency guarantees. In Ignite, there are two major cache options which you can choose in terms of consistency. There's a configuration option, set atomicity mode, in which you can pass mode, and there are two modes. First one is atomic. Atomic caches are default, and if you work with atomic caches, only entry-level atomicity is guaranteed. For example, if you perform a batch operation, if you want to put lots of entries into a cache, atomic caches doesn't guarantee that the whole batch will be applied atomically. It may happen that your put all operation will throw cache partial update exception. Most likely it will happen if server node has left during this operation. And this exception will contain a list of keys that were not updated, and you should be ready to handle the rest of keys that were not updated if that's important for you. But on the contrary, of course, atomic caches provide better performance because their network protocol is quite simple and doesn't require such complex synchronization mechanisms like two-phase commits. And other option is using transactional caches. In transactional caches, you always have ACID guarantees for your operations. You can directly open a transaction, and all updates that you have performed in this transaction will be applied atomically. So you will never get any kind of partial update exception. Either your whole batch is applied and transaction is committed, or your transaction is rolled back and none of update is applied. Transaction can be cross-partition, cross-cache. There are no limitations. You can access several caches within transaction and still gain your ACID, but the only one limitation is that in case inside transaction you will use atomic caches, transactional guarantees will not be applied to atomic cache operations. So ACID works only for transactional caches. And they are failover safe. In case any of participant transaction node will fail, you will still gain your ACID. And for example, if one node has left the cluster during commit phase, there will be a transaction recovery protocol, and all other participant nodes will communicate to each other and go to consensus on whether or not the transactions should be committed or rolled back. Next, I'll show you some cases in which transactional guarantees are mandatory, and such guarantees cannot be achieved with atomic caches. First one and obvious one is atomic batch update. When you want to update lots of keys and you want to this update either be applied fully or not be applied at all, you can open transaction, and so here's an API. There's transaction concurrency, there's isolation level, and this one is timeout. And in case your transaction lasts more than specified timeout, it will be forcefully rolled back. And you can use optimistic red committed guarantees, for example, for this case. I will share a brief summary of all differences between concurrency and optimistic modes a bit later. And what I want to say that optimistic read committed is enough for this operation. If you perform a put all or lots of puts, it doesn't matter. Under this level of transaction, you will gain guarantees that your batch will be updated atomically. And by the way, the same guarantees will be true if you just take your transactional cache and perform put all operation on it. So passing a large batch of keys to put all gives you the same guarantees like you opened optimistic or committed transaction and performed a lot of puts, perhaps in put all or as a single put. The guarantees will be the same. Second case, when transactions are required, is exclusive update. You may want to open pessimistic read committed transaction, and in this mode, when you perform a write from a put to your cache, corresponding cache entry will be locked and no one else will be able to modify it. So you may want to, for example, if you want to perform exclusive operation with user one, and during this large operation, for example, you can update some transfers, you can write some audits on this user, and during this operation, you don't want anyone else to work with this user, you can perform a put to, for example, session cache where you use user one as key, and after this put and until transaction is committed, this key will be locked. That means all other transactions with the same code will not be able to do anything with user one because they will just hang on the same put. So that means that in this window you can perform lots of your operations and you may be sure that your operation is exclusive. Next one use case, and I think it's the most classical one when we are speaking about transactions. This is safe money transfer. Imagine a situation where you want to transfer some money from account one to account two. You can open pessimistic repeatable read transaction. You can get current balances from account one and account two. And in pessimistic repeatable read mode, locks are acquired on writes and on reads. That meaning that when you performed a read using account one and account two as keys, locks on those keys will be acquired, and no other code that can perform safe money transfer will be able to perform a get on account one or on account two because these keys are locked, and the corresponding transactions will just hang on the attempt to read corresponding value. So you read current balances, or after that keys are locked, then you update values of already locked keys and perform a transaction commit. So here there's a window when no one else can access balance one or balance two. And according to that, there's guarantees that your money transfer will be safe and total sum of your money on the whole account set will be unchanged. And here I want to summarize guarantees that can be provided by different concurrency modes and isolation levels. Actually, there are 6 possible combinations, but 2 of them are redundant and just have the same behavior as another ones. So I recommend you to use only these combinations of concurrency and isolation. Let's start with here are isolation levels, and here are scenarios or guarantees which are available or not. Let's start with ACID guarantees, and yes, in every case with any concurrency or isolation modes, your transactions will be ACID, so you don't have to worry about atomicity and the partial applying of transaction results. Locks on write are acquired only in last 3 transaction modes. That means only last 3 transaction modes can grant you case when you need exclusive update. Locks on read are acquired only on last 2 transaction modes, meaning that money transfer is possible only if you're using pessimistic repeatable read transactions or mode. Practically, it gives you the same consistency guarantees like pessimistic repeatable read, but the main difference is its behavior. If pessimistic repeatable read acquires direct pessimistic locks on every read and every write, when lock is acquired, no one else can read or write corresponding key. Optimistic serializable transactions acquire only optimistic lock. That means when you perform a read, for example, no lock actually is acquired on primary node, but client also with the key and its value reads version of entry which was visible to this transaction. And on commit, if version that was visible to optimistic serializable transaction has changed, the whole transaction will be rolled back, and transaction will have to process transaction optimistic exception, meaning that your optimistic lock-in was unsuccessful and you have to repeat your transaction, and perhaps next time you will be lucky. And summarize this, optimistic serializable transaction can be forcefully rolled back on concurrent update. So when you execute commit on this type of transaction, you have to be ready that your transaction may throw optimistic exception, and these types of transactions will never behave this way. Either they have acquired all locks and are ready to commit, or they just hang in attempt to acquire a lock. And other interesting option of optimistic serializable transactions that they totally deadlock free. So consider a money transfer case and imagine that there are two transactions that read values on balances in reversed order. For example, transaction 1 reads balance 1 then balance 2, and another transaction reads balance 2 then balance 1. This transaction may be deadlocked, so they both hang on this line because there's a mutually there's a case when there is a cycle in wait for graph for these transactions. And optimistic serializable transactions, first of all, will not hang on this stage because no actual locks are acquired on reads and will not hang on commit. Actual locks are acquired if you're using optimistic serializable only on commit phase. And when you will attempt to acquire locks for balance 2, in case there's a cycle, transactions will be rolled back because it will notice that there's another transaction that have attempted to acquire a lock. So you may be sure that deadlock caused by application by incorrect lock order will never happen in optimistic transactions. And if you are not sure and you are not able to provide strict order on your keys in transactions, perhaps using optimistic serializable would be a good choice. But on the contrary, as a negative option, you have to catch and process transaction optimistic exception. I think that's it about transactions. And as a last point, I want to mention how transactions works under the hood. Transactions works with the two-phase commit protocol. When you perform during phase when you only acquire locks and when you don't perform commit, locks are acquired only on primary nodes. But when you perform a commit, there's a two-phase operation called two-phase commit. First stage is prepare, when you go to every node, including primary and backups, and acquire logs there. And after all acknowledgements and that all logs are acquired, they respond to transaction coordinator, and it responds everyone else that commit phase can be processed now. And after that, logs will be released and your transaction will be over. Speaking about transactions, this is only tip of the iceberg, I want to say. And at June 10th, I will present a next webinar about deep dive into transactions. We will overview how transactions work under the hood, and I will talk more thoroughly about interactions of transactions with other parts of system, how to debug transactions, how to be sure that your transactions won't block other operations in your cluster. So all this stuff will be in my next webinar. So if you're interested in Ignite transactions, please consider attending it. And I'll proceed. And to sum it up, if you want to choose between atomic and transactional caches, In common case, you can choose atomic because performance in atomic case is better. But in case there's a business operation that requires strong consistency, or you anticipate that such operation will appear in your system in near future, you have to use transactional caches. Because on atomic caches, there's only entry-level atomicity guarantees, and on transactional caches, there are full ACID guarantees. Let's proceed to data storage and data storage consistency guarantees. I will start with a bit unrelated to our current topic explanation of how data storage works and how it can be configured. I think it will take 2 or 3 minutes, and then we'll proceed to consistency. Apache Ignite has a multi-tier storage, meaning that your data can be stored either only in memory or both in memory and on disk. And if in case you are using persistent clusters, only hot subset of pages is present in memory, and all subset of pages will be present on disk. If you're using in-memory caches, data are stored in pre-configured heap region. Your data will not be kept on heap. So in order to be free from large garbage collection overheads or just heavy GC pauses, and you pre-configure in advance your size of this region, and in case your region overflows, you may get Ignite out of memory exception unless you have set an eviction mode, which specifies a policy or how to remove your data if you are close to capacity limit of your data region. Other option is persistent caches, when data are stored in pre-configured heap region and are synchronized with disk asynchronously, and overflow in such case will not cause Ignite out of memory exception. It will just trigger replacement of colder pages from heap storage to disk. Here is example of data storage configuration. There's a bean called data storage configuration, and there's default data region configuration. So if you will create a cache and you will not specify which data region you should use, this cache will reside in this default data region. And also you may specify some other regions, and these regions should be named. You should pass a name, for example, hot in this case, to your separate data regions, and you can pass this name to cache configuration, meaning that this cache will reside in exactly this data region. Let's consider a simple example. For example, you have hot and cold data, and you want good example is operational and historical data sets. Your operational data should be accessed fast because you want low latency on your operational data, and historical are just collected in order to be accessed later during some analytics. And a good solution would be keeping in-memory region for hot data to gain minimum possible latency, and persistent region for cold data. You can configure it this way. You can specify 2 regions, set size of historical region as 45 gigabytes and enable persistence, and set size of in-memory region as 15 gigabytes. You haven't passed persistence enabled flag true to this region, so it will be in memory, and you have to specify a name. And imagine that you have 3 caches, cache A, cache B, and cache C. And in case you will pass hot as a data region name when you create cache C, it will reside in memory region, and caches A and B will reside in default persistent region. And in case these caches A and B will overflow specified region, replacement will be triggered, so cold pages from this region will be replaced to disk. On architectural level, Ignite persistence is implemented with classical checkpointing algorithm and write-ahead log. So there are so when we perform an update, first of all, it's stored in RAM, and it's instantly in a synchronous way persisted with write-ahead log. And after it went to write-ahead log, you receive an acknowledge that your update is processed and will not be lost. Actual data storage to partition files. So when you perform an update, it's either present only in write-ahead log, or it's later will be checkpointed and synchronized from RAM to your regular data storage. This operation should be synchronous in order to, if you want to, don't lose your updates at any stage. And checkpointing is internal system maintenance procedure of synchronizing dirty pages from RAM to partition files. And speaking of consistency guarantees and performance, when you work with cache, you can configure policy with which you do this stage, in which you persist your update to write-ahead log. You can specify policy for write-ahead log updates with method set while mode in data storage configuration. And there are three possible modes. First one is background, when updates are logged to WAL file asynchronously. So this picture will not be true. So persist phase will be moved aside from update acknowledgement loop. And in such case, you will be, there's a chance that your updates may be lost, if not will crash. Second and default option is log only. In this option, updates are logged to WAL file synchronously. So exactly this picture explains system behavior for log-only mode. Last option is sync. In this option, updates are logged to WAL file synchronously as well, and even though and more than that, they are synced with storage device synchronously via sync call. Sync is system call which drops your page cache of operational system and make sure that your updates are actually present on your hardware device. Let's consider possible failover scenarios, and let's take a look whether or not part of your updates can be lost if you're using one or another WAL mode. If you're using background, in case your process will crash, this may happen if you will kill it with kill -9, or in case your node will crash with a critical failure, for example, or perhaps operational system or OM killer will come and kill your process. And other scenario is power loss. For example, if there's total power outage in your data center or your operational system, which is unlikely but can happen still, in case your operational system crashed. If you are using background mode, you may experience lost updates in both scenarios. If you are using default log-only mode, if your process will be crashed or killed -9 or killed by operational system, you will still have a guarantee that your updates will not be lost, because if updates were written to file but still kept in page cache of operational system, when process crashes, operational system guarantees that all unswapped pages will be eventually synced to hard device. And if you're using sync mode, doesn't matter. Either your process will crash, either you will lose power or experience crash of operational system. All updates will be synced to hard storage device, meaning that you will not lose your updates in any case. I want to also to add that log-only is default mode, and I recommend to use log-only mode practically in every case. And because we're working in a distributed system, and it's enough for keeping data safe in practice, because power loss or operational crash is really unlikely scenario, and most likely it will happen with only part of your cluster or only with one node. And in case that indeed will happen, your data consistency among the cluster will be restored through rebalancing. If crashed node will return, Ignite will detect that its partitions are outdated, and during the balancing process, actual data will be transferred to node that experienced power loss or operational system crash. In this, that's why I think log only is enough. And of course, if you want to extra safety, you may consider using sync mode, but you have to be aware that performance is way worse in this mode. Sync calls are really heavy, and I think there will be a 3, 5, or perhaps even 10 times drop down in your throughput if you're using sync mode. Well, I think that's it. And as a summary, I want to show my agenda for today's presentation again, and also mention some keywords which can help you to understand differences in possible Ignite configurations and main terms that should be required to configure your system. So if we are talking about data replication modes, main keywords are partitioned or replicated and set backups. If we're talking about sync guarantees, you have to choose between primary sync or full sync. And regarding data consistency, there are two main options, atomic or transactional. And regarding data storage, if you are working with persistence, I think very important keyword is baseline topology. I haven't mentioned it today, but I recommend you to read about baseline topology if you are going to work with persistent Ignite cluster. Configuring data storage and managing its capacity can be performed with data storage configuration, and if you want to tune your disk-based consistency, you have to refer to val mode. So you can consider this slide as a cheat sheet with the necessary terms to consider before you plan your architecture and plan to go to production. Well, that's it. Thanks for your attention. Now I'm totally ready to answer your questions.
Awesome. Thanks, Ivan. Just before starting the questions, I wanted to mention that I posted the link to Ivan's next webinar on the chat. So, check that out. And while you're on the topic, we have a webinar scheduled with our founder and CTO, Nikita Ivanov, for next week. I'll post a link for that webinar on the chat as well. So we hope to see you there. All right, let's get started on the questions. We have quite a few, actually. I guess let's start with this one. For transaction caches, is the entire cache locked, or is there a row level lock?
It's row level lock. When you perform a put, your key is locked, and then no other transactions can access this key, but yes, they can access other keys that are not locked by previous transaction.
All right. Another question is on replicated sync mode. Do these transactions span across all nodes?
Yes, if you're using transactional combination with full sync and with the replicated, that will mean that all nodes in cluster will participate in your entire transaction. So prepare commit phase will include messages, prepare commit messages between all cluster nodes. But yes, so you can experience quite a latency if you're using transactions over replicated cache, but it's still okay because only necessary keys will be locked.
Cool. There's a question about use cases. Please share any use cases on transactions with real-time streaming. Do you have any examples to share?
Well, I don't think that I understand what it is exactly wanted in real-time streaming. So real-time means that you want to have extra low latency. Well, but basically, if you want to stream, perhaps this is a bit out of scope. If you want to subscribe for some topic and you want to stream your data to Ignite, perhaps a good option will be using data streamer with possibly with custom stream receiver. You can specify a stream receiver in which you will process stream data as you want. So I think if you want to fuse it with transactional guarantees, I think you can just implement transaction in your custom stream receiver. I think this is a complex topic, actually. So I think you can discuss this example on user list, for example, just in case.
Can you use ACID transaction mode on large number of partitions to simulate and analyze blockchain node synchronization commit protocols?
You totally can use your transactions over any number of partitions if you want. There is no limit. You can access all your partitions in your transaction. You can even access all your data set, but you should be aware that there might be some throughput issues, because when you update large data sets inside your transaction, keys will be locked for a period of time, and in case any other transaction will access the same keys, other transactions will hang until these keys will be unlocked by previous transaction.
All right, so another question is on, can I use Ignite to replace analytical database like Redshift? Would it suit well? Would you gain speed or have any cost reductions?
Well, by meaning analytical data, well, for me, analytical database is a database where your data is more or less is not changed frequently, and you want to execute complex queries with SQL engine in order to calculate your analytics. So I think this is mostly a question on Ignite SQL engine and its capabilities. Some analytical queries, if they are not too complex or if your cluster is properly tuned, will work fine on cluster, but Ignite SQL is not really good in ad hoc queries. If you want to execute complex query with lots of aggregation functions on or join, you have to collocate your data previously. Otherwise, your query may be slow. And regarding transactions and analytical database, you have to be aware that Ignite SQL itself is not transactional. When you perform an update with, for example, with GDBC, when you perform update of your table, you will not get ACID guarantees. They will work. SQL updates will work more like with the atomic cache guarantees.
Great. There's a question, are there any performance benchmarks that are available for Ignite transactions on SQL?
Well, I can't show you graphs so far. From my experience, when you compare atomic and transactional caches, transactionals are slower and probably 2 or 3 times slower, because you need external synchronization for transactional guarantees. And total performance will certainly depend on your hardware. How good is it, and how good are your disks if you're using persistence? In our lab, cluster of nodes can easily maintain tens of thousands of transactions per second. I think this number, you can use this number as baseline, and it will be modified depending on how big your transactions are or how good your hardware is.
When I have to sync 2 systems over a defined frequency, from primary system to secondary, using a batch sync, do I need atomic or transactional processing?
I didn't get what are 2 systems. If this system somehow can be linked to Ignite caches, actually, when you use transactions, they cover only that data updates in Ignite itself. So with transactional guarantees, you can access. You can perform batch updates on your 2 caches in Ignite, and there will be ACID guarantees. But if you're talking about external system, I think I recall that in documentation there's a section about using a cache store with transactional caches, and updating transactional cache will also perform a commit to external system with under transaction logs. So in this case, you will get overall ACID guarantees among your Ignite cluster and your other system, but this is not safe, because if transaction to your external system will be rolled back, Ignite will not be able to, to somehow synchronize with your system and roll back transaction again in Ignite. So I hope that I answered. Probably I didn't get the question correctly.
Yeah, this is from Saurabh. So if you want, feel free to ask a follow-up question, Saurabh. Can I update a single cache entry atomically without using transactional atomicity mode?
Good question. Unfortunately, no. If you are using transactional cache, all your operations with your cache will be transactional. But if you will use put, only a single put, your transaction concurrency level will be equal to, just a moment, will be equal to optimistic read committed, meaning that your locks will be acquired only on commit phase, and locks will be held for minimum amount of time. So I think it somehow will be equal to atomic update with a bit better guarantees to transactional recovery protocol, but performance of single puts will be slower on transactional cache rather than on atomic.
Okay. Another question, for Ignite persistence, is there a way to take a snapshot of the persisted caches, or the corresponding files simply be copied?
I got it. Right now in last Ignite release 2.8, it's not available. It's available in GridGain extension. You may consider using Grid Ultimate, where you can perform snapshots of your persistent caches. And right now there's a discussion on patch where you can perform a snapshot of your caches. So there's actual Ignite and enhancement proposal where pull request with initial snapshots is being discussed, and perhaps it will be merged and get into Ignite 2.9. So I think the answer is right now no. It's available in Grid Ultimate, but there's a chance that it will be available in 2.9.
Awesome. All right. So I think we're we are out of time now. We have a few more questions, but we'll if there's any specific questions, I can follow up separately as well. Thank you for answering the questions, Ivan, and the presentation. We have recorded today's session, and we will send an email out with a link in the next 24 hours. We do have a number of new Apache Ignite webinars that we've added to our website. So please take a look at those, and we hope to see you in one of our future events. Thanks, Ivan. Thanks, everyone, and have a good day.
Thank you.